Lecture 82, Archimedes' Principle. So this is a lecture about buoyancy, or why things float. Probably familiar with that, yes? So let's have a look at that. But let's start with where we left off last time, right, with our little imaginary volume of water, right, in a water tank, right? So recall that delta P, the difference between the pressure at the top of the volume and the bottom of the volume, right, was equal to rho, in this case of water, H2O, times g, the acceleration due to gravity, times delta H. Remember that rho times the volume is equal to the mass, right? Yeah. So if I take the density and multiply that times the volume, right, the volume of this little box, for example, that will tell me the mass of that box, okay? Also, remember that pressure is force divided by area, right? So I want to rewrite this. I'm going to rewrite delta P as basically F divided by A is equal to rho, in this case of water, times G times delta H, right? We multiply both sides by the area, A, and we see that right here, this delta H times A, this is just our volume, right? So we get that F equals rho H2O times volume times G. Well, what is the density of water times its volume? Well, it's just the mass, right? So this says that F is equal to mg. So we see that the difference in the pressure, right, is basically balancing out the weight of the volume of this imaginary, or the weight of the water in this imaginary volume, right? That's what it's equal to, okay? So now I want to, and we can call this, if you will, the buoyant force, okay? So this pressure differential, the difference between the pressure at the top face and the bottom face of the volume, right? Yeah. That's what creates, so there's a net force there, and that is what creates this buoyant force, all right? So now I want to imagine replacing this volume with something other than water, okay? So maybe steel, for example, or iron. Let's do iron. And also what I want to do, let's get rid of some of these markings here. So the volume that I'm taking up will be exactly the same as before, okay? Yes? Yeah. Except now this is iron instead of water. So I've replaced that little volume of water with iron, okay? You might imagine that this box is filled to the top with water, and such that when I put this little volume of iron in the middle of it right there, that some water runs out over the top, right? Yeah. And I can catch that water in, say, a tray, and then I can measure the weight of it. And I would see that it, of course, is the amount of water that would occupy this volume, right? It'd be that amount of weight, right? It's what we calculated here. Here, right? Yeah. That's how much water comes out of the box because I've replaced that water with this iron block, okay? All right. But let's put a scale up here. Have you ever seen, I think they call them fish scales. And that, of course, is suspended above it. Right? I think it's what they weigh fish with. They have the scale. You hang the fish on there, and then the little pointer, right, indicates what the weight is, and so you can read that off, right? So we want to know what is the weight of this iron block inside this volume of water. Okay? I think I can do away with this. So let me just note that the density of iron, Fe, is approximately 7,800 kilograms per meter cubed. And you'll remember that the density of water is, by definition, 1,000 kilograms per meter cubed. Okay? And so if we do a quick, if I assume that the volume of this box is, say, let's assume that it's a meter cubed. That's the volume of the water, the original volume that we had, and now it's also the volume of this block of iron that we put in. Right? Well, there's 7,800 kilograms per meter cubed. There's 1,000 kilograms per meter cubed of the water, right? So we've displaced that much water, yes? Yeah. Well, remember that the buoyant force, right? So let's draw the forces here. So we're going to have a buoyant force pushing up, FB. We have, of course, the weight pulling down, right? And then we have this, we'll call it F sub spring. I'm just going to call it F net, okay? because it's the difference in these two. All right? That's the force that the spring has. So that's what the spring is reading, right? The spring, it's a scale. I'm sorry. That's what the scale is reading, right? Usually these scales are built on springs. So you have a spring, and you pull on this line, and that compresses the spring, and the distance that it compresses is linearly proportional to the force, right? Because of Hooke's law, right? F is equal to k times x, right?
Yeah.
So the bigger the displacement, the larger the force, right? So we can measure the weight on a spring scale like this, okay? So what do we have? We've got F net equals FB. Actually, we'll probably want to make it. You can already see that the weight, since the weight is, iron is very dense, right? The weight is going to be the dominant term here. So we have weight minus what we call FB, the buoyant force, right? So the weight, right, what is W if it's a meter cubed, right? W is just going to be 7,800 kilograms times G, right? The acceleration due to gravity. Mass times that's weight, right?
Yeah.
And you might remember that from before, right, the buoyant force, right, the differential in the pressure was just enough to balance out this weight of water, right? So we can see that the water, the buoyant force, right, is going to be equal to 1,000, that's kilogram, that's gravity, 1,000 kilograms times G, so 1,000 G, okay? So the net force, right, is going to be the difference in these two, that's 6,800 times G, you see?
Yeah.
So we see that the scale is going to actually read a lower weight for this block of iron than it would if we measured it in just air, right? If we just measured in air, we wouldn't have that buoyant force pushing up on it, right?
Yeah.
And it would measure 7,800 G would be its weight, okay? But with the buoyant force, right, it's 7,800 minus 1,000, so 6,800 G, right?
Yeah.
So now I want to derive an expression that is related to the density so that we can see how to do this for any material we might want to consider. We'll write weight as rho, in this case iron, times G times the volume, right? That is the weight of the block of iron, right? Because rho times V is mass, m times G, that's the weight, yes? The buoyant force, on the other hand, is the weight of the water that was here before, right?
Yeah.
Because that was the whole point behind what we talked about last time, is that the weight of this volume of water is being balanced by the difference in the pressure at the top and the pressure at the bottom. The pressure at the bottom is greater because it's deeper, right, than the pressure at the top. And so these balance out to support the weight of that water, okay?
All right.
So here's the weight of the iron, and we subtract from that the weight of the buoyant force, which is just going to be the weight of the water that was displaced. So that's rho water times G times V. I can factor out, actually I'm going to factor out this whole term right here, right? You see that I've got a G and a V, and these are the same. The volume is the same, as I said, right? G is a constant, right? So what I want to do is factor out this whole term here. So I'll get rho Fe times V times G. Put the order a little more logical. All times, well, I have a 1 here, right? Because this times 1 is just this first term, minus, what do I need for this? I need rho H2O here over rho of iron here. You see?
Yeah.
And so we can use the density directly to see how much the weight is going to change when we suspend it inside this liquid, right? Because this first term here, that's just the weight, right, in air. So I'll write it like this: weight in air times this term, 1 minus rho H2O over rho iron, okay? And so if I plug this into my calculator, did I already do it? I will see that the net force, the scale weight, right, this is going to read, what did we get? 87%. 87% of the weight in air. Okay? So if it was a 1 kilogram block of iron, when I suspend it in the liquid, instead of having 1 kilogram times G, I'll have 0.87 kilograms times G. Okay? So it'll feel lighter. Does that make sense?
Yeah.
Is it surprising that if you were to weigh a block of iron in water that it would feel lighter?
No.
You've been in a swimming pool before, right? Do you feel like you're lighter in a swimming pool than you are in the air?
Yes.
Right? Yeah, that's because your body is a little bit less dense than water. I think it's about 980 kilograms per cubic meter is your density of the human body. If you fill your lungs with air, I think it goes down to 945 kilograms per cubic meter. Okay, so you are less dense than the water. And that's what we're actually going to talk about next, because here we have a material in here that is more dense than water, right? 7,800 versus 1,000, right? So what if we put in a material which is less dense than water instead of more, right? What's going to happen now, right? So let's change, let's consider, I'll just write another one in here. Let's consider rho for a cork. And that's approximately 200 kilograms per meter cubed. Significantly less dense than water is, okay? So what happens then? Well, now the buoyant force, right, is going to be bigger than the weight, right? Because just look at the two terms, right? This, for a given volume, right, the weight of the buoyant force is going to be larger than the weight of the cork, right? So we're going to switch these terms around. But let me write this result up over here. So for rho greater than rho H2O, the relevant result is that the net force is equal to 1 minus rho over rho H2O over rho times the weight. Now we're not going to have a scale because this thing is going to do what? It's going to accelerate upwards, right? Because the buoyant force is larger than the weight of the cork, and so this thing is going to accelerate upwards, okay? So let's see what the net force is going to look like, though, okay? So we'll call it F net again. This time it's going to be the buoyant force minus the weight, okay? And it'll be, the acceleration will be in the upwards direction. If I kept this weight minus FB, then we'd have a negative acceleration, okay? Just depends on which way we call up and down, right? Just make it easy, though, right? Like this. Just doing basically the same thing that I did before. Now we've got the buoyant force, which is still going to be rho H2O times V times G minus rho cork in this case times V times G. I'll factor out this term here, rho cork times V times G, all times, now when I multiply times this, I'll have rho H2O over rho cork minus 1. So see, it's switched around a little bit, right? So this, of course, is just the weight of the cork. We call it weight in air if you want, times rho H2O over rho cork minus 1. And what does that give us? Well, we've got rho H2O is 1,000 over 200, right? This is going to make F net approximately equal to 4 times W. Okay? So if the net force is 4W, 4 times the dry weight, right, the weight of the cork in air, then that means that F sub B, right, we have 4 times W is equal to F sub B minus W. Solve for F sub B. F sub B is equal to 5 times the weight. Okay? Just simple algebra. But we can do more with this. Now let's think about what happens. Let me just write this result down here. Rho less than rho H2O. We get F net equals rho H2O over rho minus 1 times the weight. Since there is a net force now, right, and it's acting in the upward direction, and there's nothing to, before we had the spring scale, keeping the iron from falling further, right? So it didn't accelerate. It was balanced out by the spring scale. Here we don't have the spring scale, and so it's going to accelerate up to the top. You can imagine. I take a cork, I submerge it in a tank of water, and I let go of it. It's going to pop up, right? Yeah. So after a while, it's going to equilibrate, okay? And I'm going to draw it more level because it's hard to draw a three-dimensional perspective on this. Imagine that this is the water level, okay? And we're going to have some of the cork is going to be above the water, right? And some of the cork is going to be below the water. All right? See that? Yeah. That's what happens after it, equilibrates. It pops up and it'll, bounce for a little bit and then it'll settle down, right? Now, there's going to be a fraction of the volume that's outside the water and a fraction that's inside the water. If we let V be the total volume of the cork, right? and we'll let V prime be just the volume of the cork that's below the water. Okay? So what's going on here, right, is that the cork is being lifted up out of the water just enough such that the buoyant force is equal to the weight of the cork. Okay? And it's no longer accelerating. So F net equals 0, which implies that the buoyant force is equal to the weight of the cork. Right? Well, we know what the weight of the cork is. That's just rho cork times the volume times G. The buoyant force is rho H2O times not V, because the volume of displaced liquid is only V prime, right? So times V prime times G. Okay?
Okay.
The G's obviously cancel, so I can get rid of those, yes?
Yeah.
Okay, so we get the following relationship, that V prime divided by V, just kind of cross dividing here, will be equal to rho cork over rho H2O. Or any liquid. It doesn't have to be water. It can be any liquid. Okay? It can even be air, but that's gas. We won't get into that right now. But there are buoyant forces even in gases. Okay? But because the density of air is something on the order of, I think it's a kilogram per cubic meter, right? So it's very small compared to, say, water. That it's negligible, the buoyant force that you feel in air. Okay, yeah, so what do we get for these numbers here? This means that cork is 200 over 1,000, which is water. That's 1 over 5. Right, what does that mean? That means that in the case of a cork, right, which is it's not very dense at all, most of the volume is above the water. And if you've ever dropped a cork in the water, you kind of observe that, right? Only 1/5 of the volume is beneath the surface. Right? You can solve this to say that V prime is equal to 1/5 of V, the volume. So whatever the volume of the cork is, 1/5 of it is below the water line. Okay? So it might be interesting to ask, what is it for other things, right? So if this was not, let me write this result down. V prime over V is equal to rho over rho H2O. So what would this be if this was, say, an iceberg, right?
Yeah.
So an iceberg, turns out that the density of ice is less than the density of water. That's why ice cubes float, right? They don't sink to the bottom or hover around at whatever, altitude they're at in your glass, right?
Yeah.
They actually float up to the top. And I think, as far as I know, it's the only liquid that does that. When it goes from liquid to solid, it becomes less dense. It's just the kind of the unique molecular shape of water, and probably hydrogen bonding. But anyways, so what would an iceberg be like? Well, rho of ice is approximately 0.9 times rho of liquid water. Okay? Which means that if we use our formula over here, V prime over V, to figure out what portion of the iceberg is submerged, right? This would be rho, it's going to be rho ice is 0.9 times rho H2O divided by rho H2O, which is 0.9, right? So what does that say? That says that 90% of the volume of the iceberg is underneath the water. Okay? So that's what they mean when they say that's just the tip of the iceberg, right? What that references is that most of the iceberg is what you don't see. It's under the water. Okay? Now here's a question. What would happen if I got my ice chainsaw and went out there in a rowboat and I chopped the top of that iceberg off and then put it in my boat and hauled it away?
10% of the rest of the iceberg would float up.
So the iceberg is going to float up, right? It's not going to float up to the original height that it was, but it'll be close, right? So let's say the iceberg stuck up, 20 meters above the surface of the water, and I chop that off. Maybe it's 19.5 meters above the water after I chop it off. It'll just rise up, okay?
All right.
That's kind of cool, huh?
Yeah.
I mean, I suppose you could try this with an ice cube. It wouldn't be hard to do that. Well, I guess it's not that easy to cut ice. You have to get a saw and a cold room to do it in. But anyways, so this, of course, doesn't represent 90%, right? I have to draw something, a big box. Most of the iceberg is down below. Let me see if I can draw something to that effect. Here is an iceberg. There we go. There. There's the water level there. Okay? Yeah?
Yeah.
So if you wanted to tow an iceberg and you thought, well, it's not that much ice, just a little chunk like this, you got all this you got to drag too, right? That's why if a ship hits it, it's not like hitting a little block of ice, it's like hitting a big block of ice. Okay?
Okay.
Inertia is not your friend in this case. It's going to, even if you've got a big ship, this is a big piece of ice. Okay? But it's also true, ice is not the only thing that does this. There's an interesting difference in density between the crust, the Earth's crust, and the density of the mantle, right? That's the next layer down in kind of the layers of the Earth, right? If you chop it up into pieces, you've got the core, right? Then you've got the mantle, and you've got the crust sits on top. So a mountain, of course, is Earth crust, right? Let me draw it a little bit different. So something like this. There we go. So this is the mantle. This is the crust. And this is one of those things they call mountains, right? So if rho crust is approximately 85% rho mantle, that means that V prime, the portion of the mountain that's below the surface that you can't see, right, is 85% of the total volume of the mountain. So the total volume of the mountain is all this that you see here. This is the mountain. But this little bit up here is what you see when you're walking on the land, right?
Yeah.
You just see that little bit bulging up. 85% of it is submerged in the mantle, right? Remember, these are rocks. They're hot, but they're not liquid, okay? I'm not talking about magma here. This is the Earth's mantle. So on the scale of geologic time, though, these are like liquids. They kind of flow. And buoyancy is what holds this mountain up, you see?
Yeah.
If I were to chop the top of this mountain off, right? I think the Soviets actually did this. They leveled mountains by blowing them up with nuclear weapons. Now, why we do that, I don't know. But I guess if you want to put a train track through there or something, who knows? But on the scale of geologic time, this is not a good idea because what's going to happen? It's going to be just like the iceberg. You chop the top of this thing off, and it's going to buoy up more, and so you're going to get mountain again. This is why mountains are so slow to erode away. Right? We always have erosion. There's always rain and wind, which is taking away the top layer of everything, right? And so you think that after millions of years, or hundreds of millions of years, that mountains would just erode away, right? Kind of like land does. You've seen the Grand Canyon, or at least pictures of it, right? I think this is largely erosion. But because as you take stuff off the top, buoyancy pushes more up from the bottom, okay? Because this crustal, the Earth's crust is floating on the mantle. That's why it's there, okay? Because it's buoyant. It's less dense than the mantle. Make sense?
Yeah.
Interesting?
Yes.
Somewhat, right? Okay, I think that is all I have to say about Archimedes' principle. I could relate the story, although I don't know exactly how it... The story I remember is that Archimedes was given the task of determining whether or not a crown was truly made of gold or not. And so the problem is, they knew what the density of gold was, but the problem is the crown is oddly shaped, right? It's hard to get an accurate volume measurement on that, right? But Archimedes apparently, while stepping into the bath one day, noticed that the volume, right, would be equal to the volume of displaced liquid, right? So when you get in the bathtub, if the bathtub is too full, water flows out over the side, right? How much water? Well, it's equal to the volume that is being displaced by your body getting into it. So if we can take a vessel of water and dip the crown in there, there will be water that's displaced, right? We know what the density of the water is. We can figure out what the volume would be. Okay, now we know what the volume of the crown should be. We can measure the weight of the crown. Now we know what the density is, and we know if it's gold or not. Okay?
All right.
Now how that exactly relates to the Archimedes principle, which basically says that, so Archimedes principle, I guess I should finalize, end with that, the statement of Archimedes principle, which I never actually did. I have to think how to state it. The buoyant force is equal to the weight of the displaced water. That's my simple version of it. I think that is accurate. If not, then I'll add a little thing to the video to clarify, but I think that's accurate. I think that Archimedes' principle basically says that the buoyant force is equal to the weight of the displaced water. So for any volume that we wish to consider. Okay?
Okay.
That's it. Next time we'll talk one more topic in liquids. Though there's plenty to talk about in liquids. We could spend a whole, make a whole course on liquids. Very complicated stuff. But we'll talk about Bernoulli's principle, and that will be a fun one too. But that'll basically be where we end it with liquids, and we'll move on to gas next week. Okay?
Okay.
All right.